Okay, last up in this chapter section. We're asked here to graph a geometric sequence, and we're given a word problem here. It says a tennis ball is dropped from a height of 12 feet. Each time the ball bounces back to 80% of the height from which it fell. Draw a graph to represent the height of the ball after each bounce. So we're looking at a geometric sequence. We're going to graph it. And if I were to write this as a function, let's say, well, I'm going to just do it like this. We got AN equals A1 times common ratio raised to the power of n minus 1. And if I were to write that as a function, let's say I would write this as f of x equals A1, once I determine A1, times the common ratio raised to the power of x minus 1. All right, so let's think here. The ball's dropped from 12 feet, and each time the ball bounces back to 80% of the height from which it fell. So I'm interpreting here that the common ratio is going to equal 80% or 0.8. It's going to be the common ratio. And it says to draw a graph to represent the height of the ball, and this is critical right here, after each bounce. Now, I might be tempted to think that A1 is 12, because I'm given that it's dropped from a height of 12 feet. So here let's say we got the tennis ball. It's up here at 12 feet, and it is dropped, and it bounces back to about 80%. But notice here it says draw a graph to represent the height of the ball after each bounce. And that after each bounce means that I've got to figure out what the height of the ball is after the first bounce. In other words, A1, this is going to equal A1 when it bounces back. So I'm going to go ahead and take 12 times 0.8. We'll put it in parentheses, make it look better. And when I figure that, 12 times 0.8 is going to be 9.6 feet. All right, so I'm going to write my function equation here now. And that is f of x is equal to 9.6 times 0.8 raised to the power of x minus 1. All right, let's go over and graph this thing and see what it looks like. What do you think? All right, so we got a function. We figured a function equation of 9.6 times a common ratio of 0.8 raised to the power of x plus 1. So let's then enter this into our y equal. So I've got 9.6 times, and I'll put this in parentheses, 0.8, that represents the 80%. And we're going to raise this to the power of x minus 1. X is our independent variable. Y is our dependent variable. Now, before I go and look at the graph, I'm going to make some adjustments in my window setting. Okay, let's see. X minimum. Okay, I've got that set right now at 1. I'm going to leave that there. 10 is my x maximum, my y minimum. 0, I'm going to leave that there. And I'm going to change the y maximum to 12. That's because we're dropping this ball from 12 feet. And we know after the first bounce, it's at 9.6 feet. And let's go in here and take a look at our graph and see what we look like here if we've done this correctly. Okay. And so after the 10th bounce, we're down there. Let's see what we got here. So when y, remember we set our x minimum to 1. There's our first bounce. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, about 9.6. And we can see that it's we've got an exponential function. In behavior is decreasing out to infinity. And when we get to about 10, let's see, we're probably somewhere a little less than 2 feet. Let's go look at our table and see what it shows us. All right, so there's at 0. There's where we dropped it at 12. After the first bounce is 9.6, and we get out here to the 10th bounce, and we're 1.29 feet if I round that off to the nearest hundredth, or 1.3 feet. All right, looks pretty good. Go back here and look at our graph again. There we go. We graphed the function 9.6 times 0.8 raised to the power of x minus 1. We have graphed a geometric sequence. How about it?